right, welcome back. This is part 3 of the Ecart review problems, and number 12 has some definitions that we haven't talked about in a little while. So the roots, remember that the roots they can be real or imaginary. If they're real, they're on the x-axis, and in this case they are real. They are -5, 2, 1, and 6 is a double root. So -5, 2, and 1 are single roots, and 6 is a double root. So first we have to remember terminology. So a double root would have bounce off the graph. Anytime you see a double root, when you're going to graph it, you're going to see it bounce off. And could be a parabola, or it could be like this function have other things happening, but a double root is when it hits the x-axis and bounces off. A single root will go straight through. So here would be a single root. And then a triple root has that twist in the curve there. So remember, a triple root looks like this, and it'll definitely twist. It won't go straight through like a single root. Okay, so just in case they have triple roots tomorrow on the Ecart, wanted you to see that. In this example, we only have a double root and single roots, but a triple root would twist through the x-axis. So if it says on the graph below to graph a function with the roots described, we could have two different kinds based on our end behavior, but either way both should have a point at these values. So -5, 0, -1, -2, -3, -4, -5, and then 2, 0, and then 1, 0, and then 6, 0. 1, 2, 3, 4, 5, 6. Our double root is going to again bounce off, and I should move that over more. It's a little too off. There, that looks better. And our single roots will go straight through. And here's one example with different end behavior. Go ahead and try to come up with a second example and match. Okay, so another example would have the double root bouncing off this way with the opposite end behavior, and then going through these single roots. Okay, there could be different max and mins based on what you drew, but the roots should all be in those spots, and it should not go through for the double root, but go through for the single roots. All right, for questions 13 through 15, they want us to use these functions. So our first question is asking us to find the inverse of g of x graphically and algebraically. So our g of x function is the square root of x minus 1. And we can use transformations or a calculator to graph this. And remember, this would be our h, and would be 1. So we would move our square root function to the right one, and that would be our endpoint. And our next point would be here, and then our third point is 1, 2, 3, 4, up 2. So remember that for transformations. When you're using to find the inverse graphically, it's helpful to write out the points. So I'm going to go ahead and write down those points and then talk about the inverse. Okay, so this is graphed our g of x function. With our g of x function, we now want to graph the inverse. So I just put the points down on our x and y, because when we have the inverse, what you do is you're reflecting over the y equals x line, and you're switching your x and y values. So for the inverse, it's going to have it's going to be the point 0, 1 instead of 1, 0. And then the next point for this one would be at 2, 1. So my inverse would actually be at 1, 2. And then our last point here is actually at 5, 2. I wrote down the wrong thing here. So 5, 2. And the inverse would be at 2, 5. Okay, and then we draw our graph, and there is our inverse, and it's graphed over the y equals. So here's our y equals x line. That it's so the inverse is a reflection of the original graph over the y equals x line. And you find that by switching your x and y values from the original graph. So the same thing can be done algebraically. And our first step for algebraically would be first to realize that g of x means y, and then we're going to switch x and y. Now we're going to solve for y. So to solve for this y, I have to square both sides. And we'll get x squared equals y minus 1. To get y by itself, we have to add 1. So our inverse of our g of x is x squared plus 1. But notice how it would, because it's the square root, the inverse of it would not include that whole parabola. So we would want to write the restricted domain of, so x would have to be greater than or equal to 0, because our square root is only showing the positive square root of x minus 1. So my inverse would be this half of that parabola that we found algebraically. So x squared plus 1 of all the x values greater than 0. Alright, our next one is composition. Notice these two are compositions. And remember, composition is putting one function inside the other. So for 14, we're going to put the g of x inside of f of x. So we always work from the inside out. So our g of x function will go inside the f function. So first we substitute in what that g of x function is. Now we take that and it's going to replace all of the x's in f. So I'm going to take that square root of x minus 1 and replace it, this x with that, and we'll be left with 2 times the square root of x minus 1 plus 3. Now we look to simplify, and in this case there's no like terms, so that would be the final answer. Our second problem is saying find h of f of x. So now they want us to put f of x inside of h. So we start off by, again, working from the inside out. F of x is 2x plus 3. Just got that from our bank of functions here. And now I'm going to put 2x plus 3 in place of all the x's in h. So only the x goes away, everything else stays the same. So we have 3 times 2x plus 3 squared plus 1. Okay, so here's interesting. We would have to FOIL this first. We have 2x plus 3 squared, then multiply by the 3, and then we'll have to add 1. So there's some good Algebra 2 for you here. Remember, we have to do the exponent first, and now we're going to multiply 2x plus 3 times 2x plus 3, and that would be 4x squared plus 6x plus 6x plus 9. then we combine like terms, and then we'll multiply by that 3. And then we'll add the 1. Don't forget that 1. So that's just multiplied by the 3, and then we have to add 1. So our final answer is 12x squared plus 36x plus 28. Okay, so that one was a lot longer than the other. And you never know with composition. They could be simple, like the number 14, and just have a couple steps, or they can be a little longer, number 15. All right, let's look at our last problem, number 16. And we want to graph our cube root and then talk about the characteristics. So let's try this with the calculator, and just make sure you know how to put the calculator in with the cube root. So let's clear out the functions from last problem we did together. And for the cube root function, remember we're going to hit math and then go down to number 4. And then we want to hit x plus 1. Now, if your calculator is like mine, you need to make sure you close that cube root, because the minus 2 in this equation is on the outside. Okay, so make sure you close it just whatever's on the inside of the cube root, or if it was a square root, and then put any of the rest of the equation. Now we're going to graph it. And there's our cube root function, minus 2. And you can use your table to go and graph it on your paper. I'm going to go ahead and use transformations. I'm pretty used to the transformation. So it moved to the left 1 and down 2. And then remember my parent graph. Okay, and just to get an accurate graph, you can use the table or your parent graph. So there's my cube root function of f of x. For my domain, remember we're talking about the x values, so we're scanning from left to right, and we write it from low to high. So our graph is continuous, there's no holes in our graph. So, and this arrow is going to the left forever. So the values out here, remember, this would be -1, -2, and then it would go all the way out to -infinity. So our domain would be -infinity. That's the least value, and then all the way, it continues the whole way through, all the way to positive infinity. Our range values are the y values. So again, we write them from low to high. So for the y values, when we're going this way is our lowest. And this arrow clearly is going to the left, but it's also slowly going down. So it would include all of these values and would keep going down. So, here would be -1, -2, and would keep going down all the way to -infinity. And then again, the graph is continuous. And the y values would, just like this arrow is going to the right, it's also going up. So it would include all of these y values to infinity. Okay, our x-intercept, we can use our table to find that. And we can also plug in our, set our y equal to 0 to find that. Either way, we're going to get 7 as our x-intercept. And our y-intercept, we can clearly see on the graph, is -1. So that's 0, -1. And for this graph, for increasing and decreasing, we're starting our roller coaster and seeing what's happening. Our graph from left to right would always be increasing. So they're increasing, we're writing down in the x value, so that would be -infinity to positive infinity, and then there would not be any decreasing. Okay, end behavior, go ahead and take a minute to try that and bring it back. Okay, so remember we're talking about the left and the right side of the graphs, and the left side of the graph is going negative infinity, and the function on the